on Zoom, when you go to the seating chart, you put your name over here that says I am on Zoom. So you do still have to fill out the seating chart. Don't forget to do the seating chart. Okay, masks up. How y'all doing today? I think that's the feeling for the whole semester. Feel y'all. I got 2 more minutes. Did y'all go and get fed in the quad? Wear red to get fed? I didn't even know they were doing that.
Wait, what? I couldn't.
Well, yeah, so, well, they might still have some after class. You go by, it's pizza. They have pizza in the tent in front of the education building. It's what, it ends at 1? Oh. Oh. Well, I hope y'all got lunch then. All right, so what did one plate say to the other plates? Dinner's on me. All right, so I know you can tell I did not bring in the exams today. I'm going to bring in the exams for y'all to look at on Thursday, because I still have a few that are coming back from Student Access Center and stuff like that. So I will bring them all together on Thursday, but the grades that I already have are posted. Y'all can see them, right? Yes. Okay. So I will bring them next time. Okay. Any questions about that? Okay. All right. So we need to finish chapter 5, right? We have a little bit of chapter 5 left. We're going to do a couple of quick clicker questions. These should be really easy because they're on chapter 5. I'm not going to give you any on chapter 6 today, but I will give you some on chapter 6 on Thursday. So let's see. I want this one. Okay, so this should be really easy. Some easy ways to get a few points on iClicker. Oh, but I got to start iClicker. Hello.
I was like,
You're like, but it's not on. That would help, wouldn't it? I thought I had everything done. You have an exam one day and you get out of the habit. And iClicker actually takes the longest. And so it's usually one of the first ones that I'll pull up because it takes forever. Okay, let's see. What letter of the alphabet has the most amount of water? The C. I know. All right. Okay, here we go. Let's try this again. Okay. All right, so the food label has listed the following: 22 grams of carbohydrates, 7 grams of fat, 5 grams protein. How many calories are present from carbohydrates? And I did something very nice for you and gave you a little table right there to help you out. So if your best friend is not available, that's what you need. Y'all, 1:20 because you actually have to put this in a calculator. I'll give you to 1:20. Make sure you check in. Y'all know y'all get a participation point each day just for answering everything, right or wrong. It helps. Okay, so turn and talk to your neighbors and decide if you got the right answer or not. Okay, another 10 seconds. Make sure you buzz in again. Make sure you buzz in again. All right, so still got people buzzing in. Buzz in, y'all. I'll give you 5 seconds. 3, 2, 1. Okay, so what did we say? All right, B is correct. Go back and grade the other one. B is correct. The question was asking you for how many calories present from what? Carbohydrates. So if you just are looking at carbohydrates, all you had to do was convert carbs to calories, right? And so here's our carbohydrate, and we know we get 4 calories per gram. So 22 times 4 is 88. Yeah. Now, why am I giving you one that you just had an exam on? You're still responsible for this material come the final exam. The final exam is cumulative. Okay, so don't be like, oh, I'll never see this again. Yes, you will on the final exam. So don't, if something didn't stick, come get some help. All right, we're gonna do 2 more and then that's it today. All right, activation energy is what? What is activation energy? Mass over noses and mouths, please. Okay, 10 seconds. Okay. Turn and talk to someone by you. Please keep those masks over your noses and mouths as you discuss. Oh, I'm supposed to call it at 30 seconds. Y'all, 10 seconds. Everybody buzz in. Okay, everybody should be buzzed in. Okay. So what do we get? That is not, that is the old one. Oh, we're quite divided on this one, aren't we? We're quite divided on this one. So no one thinks it's A and no one thinks it's B. So our majority are D or E. If it's E, all the statements have to be correct. If it's D, if A, B, or C is incorrect, then it has to be E, right? So if it's E, everything has to be right. If it's D, A, B, and C are all three are incorrect. So activation energy is high in reactions that progress slowly. If the hill is really high, does Dr. B want to ride the hill? No, that's a whole lot of activation energy, and I don't want to put forth that effort to do it, right? So is activation energy high in reactions that progress slowly? It is. Can you affect your activation energy with the presence of catalyst, right? This is what we were drawing here, right? If you have this particular reaction, here's your activation energy from here to here, right? If I add in a catalyst, whoa, look at that. I can really drop my activation energy. Y'all see that? So is it affected by the presence of a catalyst? Yes. If you can mark any two correct, what has to be the right answer? It has to be E. I'll talk about each one, but that's a test taking skill, right? If you see that and more than one is correct, they all have to be correct. So the difference in energy between the reactants and the highest point on the energy diagram. Here's the reactants. Here's the highest point on the energy diagram for the uncatalyzed and the highest point on the catalyzed. That's the definition of activation energy, right? So it's really big in our uncatalyzed blue, and then it's lower in our catalyzed red. Is activation energy the amount of energy that must be attained by reactants for a chemical reaction to occur? If I never get to the top of that hill, am I ever going to go down it? No, right? So it's the minimum amount of energy that those reactants have to get. So the answer to that one is E. Oh, let's see. We went up at least. We went up at least. Okay. Last one. Last one. So which of these changes will increase the rate of a reaction? Which one of these changes will increase the rate of the reaction? Okay, 10 seconds. Turn and talk to the people around you and guess again. Okay, don't forget to buzz back in. I'll call it at 40 seconds. So you have 10 seconds remaining. Five seconds. Okay, so which will increase the rate of the reaction? Let's see what y'all said. C is correct. C is correct. We went up quite a bit. That's great. So if we decrease the concentration of the reactants, it's just like having fewer cars on the road. So what happens when you have fewer cars on the road? Fewer collisions, right? Fewer collisions. So what happens to your rate? You decrease the rate, right? So A is not correct. If you lower the temperature, what are you doing? You're decreasing the speed of the molecules. So this is like you have cars on the road, but they're going really slow. Are they going to end up colliding with one another? Not very much, right? So here we're going to, again, decrease the rate of the reaction. So it can't be that one. If you add a catalyst from the previous question, what happens? You increase the rate of a reaction, right? Because you decrease the activation energy. So it can't be D and it can't be E. So it should have been C. Okay, good. Nice little review there. All right. So let's go to our problems. We're going to go on to section 5. Section 5. Yep. So section 5, chapter 5, section 5. Section 5, section 6. It's just 2. Yeah, it's just 2. Will be on the next exam. Okay, so this starts our material for our next exam. And it kind of goes hand in hand. It's actually not a bad thing. All right, so we're going to start talking about all kinds of different reactions that are going to happen to carbon-containing molecules. And we're going to talk about this for quite a while because there are a ton of different ones. So we're going to kind of start simply and then get to more and more complex things. So one of the most common things that happens to organic molecules is that they undergo what are called condensation and hydrolysis reactions. Condensation and hydrolysis. So when I think about condensation, right, what do you think of? I think I have a nice big glass of iced tea and I put it down on my counter and what happens? Water forms on the outside of my glass, right? So this is kind of how I remember condensation, is this fact that water forms, right? So this is going to be a little way to remember what's happening. And condensation and hydrolysis are the opposites of one another. So what does hydro mean? Water. What does lysis mean? Lysis means to break something, right? So in hydrolysis, we're going to break water. In condensation, we're going to make water. Okay, so this is the way you kind of remember this. So what type of chemical reaction is condensation? Well, to know what that is, you kind of have to be able to draw a general reaction for condensation. So if I have 2 molecules, right, they have an R group, and then they have this. What is OH? What functional group is that? A hydroxyl, right? Remember this, an alcohol, either way is correct. And if I have another molecule that looks just like this, but in this case, I'm just going to position it differently. Do I still have a molecule with a hydroxyl? Yes. Yes, I just drew it differently, right? I just arranged it differently in 3 dimensions. So if I take this molecule and I combine it, that's what condensation is. I'm going to make a new molecule and I'm going to make water. I want to make water first and then see what's left. So what is water? H2O. So I'm going to need 2 hydrogens and 1 oxygen. I'm going to take the hydrogen, 1 hydrogen from one molecule, and I'm going to take 1 hydroxyl from another molecule, and I'm going to combine them. So I'm going to take, for example, this hydrogen right here, and I'm going to combine it with this hydroxyl. Do I have H2O? Yes, I do. This is just another way to write H2O, HOH. It's the same thing. So I'll just put it in parentheses so that we remember that. Okay, now what do I have left? Go from left to right. I have an R group in red, right? Okay, do I have anything attached to the R group? I have an oxygen. I have an oxygen. This is what's left. So I have an R group attached to an oxygen. Now pick up what's left in the blue. What's left in the blue? Just another R. So I'm going to go RO, and then I'm going to bind that to my other R. Do you see how all I did was take away a water and then combine what was left? So condensation and hydrolysis are opposites of one another. So if I look at this condensation reaction, what am I doing here? I'm taking two small things and I'm making something new. So what do we call that kind of a reaction? What? It is a condensation reaction, but is it synthesis, decomposition, or exchange? It's synthesis. This is synthesis. This is synthesis. Because we are making something completely new. Look at the equation above. Look in 5.35. Do you see hydrolysis? What are we starting with in hydrolysis? Do you see this and this? Are they any different? No. So condensation and hydrolysis are the opposites of one another. Hydrolysis is going to take a molecule of something, it's going to use water, and it's going to break it up. Condensation is the opposite. We're going to have two molecules, and we're going to put them together and form something new. And the other thing is that we're going to make water when we do that. Okay? So condensation and hydrolysis are opposites of one another. Hydrolysis is decomposition, condensation is synthesis. Yeah? Okay, so let's go try some of these. Okay. Draw the products from the ester hydrolysis reaction shown. Okay. If I'm going to take this and I'm going to add water to it, I'm undergoing hydrolysis or condensation? Condensation or hydrolysis? Hydrolysis. This is going to be hydrolysis because we are taking some substance and we are adding water to it. What happens in a hydrolysis reaction? Is this a synthesis reaction or is this a decomposition? Hydrolysis is decomposition. Right? So I'm starting with an ester. What's an ester? ROR, right? It's got an oxygen in the middle of some carbon, right? Do I have that in what they've given me? I actually do. So this CH3 is an R group, and then all of this is an R group. Now, do you see the ROR? That's what you're looking for. So a lot of these equations are just identifying the bits and pieces. So you look for the oxygen that links the two parts of the molecule together. And then what's our general format for a hydrolysis? We're going to have something that's ROR. And what are we going to end up with when we add water to it? General format, just from up above. We're going to have ROH plus HOR. Yeah. Okay, so this is kind of what we want to end up with. And I think it's good to have this little formula up here. So if I start with this real product here, this is my real product. I'm going to add water to it, but I don't like to do this water the way it's written here. I like to do it as HOH, because it makes a little more sense. So what am I going to do with this water? Well, one of these R groups is going to get a hydrogen and the other R group is going to get a hydroxyl. So let's give R group 1 the oxygen. Okay, so I'm going to write R group 1. These are my products. You see how it's reactants up here? I'm just going to draw products down here. Okay, so I have CH3. I'm going to give it the oxygen, right? All I've done so far is written what's here. What does this oxygen need to be complete to undergo a hydrolysis reaction? If I just take away this part right here, that's what I just did. How do I get from here to here? What's the difference? Add a hydrogen. Where does the hydrogen come from? Comes from over here, comes from the water, right? So I'm going to put my water, my hydrogen from my water right there. That's one of my products. Now what? What's my other product? My other product is my R group, which is right here. It's this R group, which is the same thing as this R group. So how do I go from one to the other? What do I have to add? A hydroxyl group. Where's the hydroxyl group? Where do I get it from? From the lysis of water, right? From this is the remainder. I've already used up this hydrogen. What do I have left? I have the hydroxyl left. So I'm going to use the HO from water from over here, and then I'm going to put the rest of my molecule, the rest of my molecules. So I have a C double bonded to an oxygen, CH2, CH3. So here are my products. So if you want to do this in black so that you can see just where the changes happen, the changes happened here. This hydrogen came from water. This hydroxyl came from water. Y'all are super quiet today. Good, bad? What y'all think? If you draw this reaction at the top, it's going to help you remember what you're supposed to do. Okay. All right, so let's see. Next one. Oh, we're in a different section. Those were the only examples? I guess it is. Okay. So the next reaction we're going to talk about are some other organic reactions, right? Carbons and hydrogens reacting. And in this case, we're going to talk specifically about alkenes. What is an alkene? This is a carbon-carbon double bond. So in this case, what we're going to do is we're going to start adding things to these carbons. What happens when we add things to those carbons? We're going to lose those double bonds. Have you heard about hydrogenated fats before? Saturated fats, hydrogenated fats, right? All that kind of stuff. So right now you know what a saturated fat is, right? So saturated is covered in. Y'all are terrifying me a little bit. Hydrogen, right? Saturated in hydrogen, so it has no carbon-carbon double bonds. If you have something that is unsaturated, it could be an alkene because it has a carbon-carbon double bond, right? So what manufacturers, food manufacturers will do is they will actually process the food and they will hydrogenate it, which means that you start with something that has a double bond and then you add hydrogens to it to saturate it. But a lot of times in the food industry, the process is incomplete, right? And so you started with a fat that had a carbon-carbon double bonds that was in the cis configuration. You partially hydrogenate them, and then you're left with some double bonds still, and those double bonds are now in trans configuration. So this is what we were talking about before about the trans fats. Remember that? A little bit? No? So when we talk about hydrogenation, here we go. All we're going to do is we're going to look for, you're going to look for a carbon-carbon double bond. Those carbons are participating in two other bonds, right? There's a double bond between them, and they're participating in two other bonds. So what we're going to do is we're going to add hydrogen to each carbon. If I do that and I leave the double bond, how many bonds would carbon have? If I just took this carbon and I added another hydrogen, count up how many bonds? 5. Is that okay? That is not okay, right? So basically, we're just going to add hydrogens to each carbon, but then this is wrong, right? You can't have a double bond, so it turns that into a single bond. Hydrogenation is super easy. You're looking for H2 being added to a molecule that has a carbon-carbon double bond. And usually it happens with a catalyst. And in this case, it's a platinum catalyst. This is just a metal catalyst that's going to give a platform for that reaction to occur. So all you have to do to draw the products is to add a hydrogen to each carbon and remove the double bond. So I don't know how I did this, but I'm going to draw the products over here. So I'm going to draw the products over here. Here are the products. Just because for some reason I'm on the wrong side. So I'm going to draw my carbons that were participating in the double bond. Take away their double bond and give them a single bond. Then 3 things around them, right? One of them was a hydrogen. Another was a hydrogen. And this last one, all you have to do is pick up what was already there. So C, CH2, CH2, 3. Do you see that? All I did was copy what was here, right there. Now I'm going to do the same thing for the other carbon. I'm going to give it 3 things around it. One of them is the hydrogen that's already there. Another one is the hydrogen that I'm adding because I'm undergoing a hydrogenation reaction. And the last one is going to be the same thing that's right here. CH2, CH2, CH3. So I lost the double bond and each carbon gained a hydrogen. So for a hydrogenation reaction, look for the carbon-carbon double bond, add a hydrogen to each carbon, and then remove the carbon-carbon double bond to make a carbon-carbon single bond. All right? Let's look at the next one. Ooh, this is a skeletal diagram. It's kind of easy to do skeletal diagrams because do we draw hydrogens on skeletal diagrams? No. So what do you have to do for this one? If I add hydrogens to each carbon, but I'm not going to show that, and then just turn that double bond into a single bond, what do I draw? The exact same thing, but no double bond. So let's draw it. Right? I go 1, 2, 3, 4, 5. Okay. And then I have one coming off on the side. And then I go 6, 7, 8. Number your carbons if you need to. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then I have this methyl group coming off, and I kept my methyl group coming off. So the only thing that's different here is that we draw double bonds as straight instead of being zigzaggy. because in 3 dimensions, they really are. And that's what changes fatty acids. So like, you know, your butter, what's your, what state of matter is your butter at room temperature? Solid. How about olive oil? Liquid, but they're both made up of fats. So butter is made up of saturated fats. So they pack together really tightly because they're these perfect zigzags, and they're all these perfect zigzags, and they stack up really, really tightly together. But then your oils have cis double bonds. And so they end up having like kinks in the tails. And so they don't stack together very nice. And so they end up being liquids at room temperature. Things you never know you wanted to know. So cool, right? Okay, let's try the next one. Now I have a ring. The same thing, it's a skeletal diagram, but I'm going to remove the double bond because I'm actually adding hydrogens to each of these carbons. So what should I draw? The same thing, just no carbon-carbon double bond. Draw my little house. It's a terrible looking house, but right? That's it, done. How easy was that? Hydrogenation, all you're doing is adding hydrogens and then losing those carbon-carbon double bonds. Okay? All right, so that's hydrogenation. Okay. Now we're going to talk about hydration. When we talk about hydration, right? If I'm going to hydrate, what do I need to drink? I need to drink, oh, excuse me. I need to drink water. It would be nice to have a little drink of water right now. So I'm going to drink water. What is water composed of? H2O, right? But in these reactions, it's been nice to write them as HOH, right? It's the same thing. So what we're going to do for hydration reactions for alkenes is we're going to have a carbon-carbon double bond. One carbon gets a hydrogen. One carbon gets, excuse me, the hydroxyl. So it's very similar to hydration, to hydrogenation. But in this case, we're not talking about adding H2, we're talking about adding H2O, and there's no catalyst. So I just copied and pasted these because they wanted you to do it with the same compounds in the previous question. So just change all these to H2O and no catalyst. Yeah. So what's going to happen to these carbons? One carbon gets a hydrogen, one carbon gets a hydroxyl. How do you know which one gets what? Look at the carbon. The carbon is either attached to hydrogen or an R group, right? Call this entire thing an R group. Whichever carbon is bound to more hydrogen atoms is going to get the hydrogen. So here's a hydrogen, here's an R group. Which of these two carbons is bound to more hydrogens? Carbon 1 is bound to how many hydrogens? Numero uno, only one. Carbon 2 is bound to how many hydrogens? One. For this one, does it matter? Nope, does not matter. You could add the hydroxyl to either one, you could add the hydrogen to either one. So I'm going to add a hydrogen here and a hydroxyl here, and then I'm going to lose this double bond. So let's redraw what that should look like. We have a hydrogen. Oops. Let's start with the carbons. So here's a carbon, here's a carbon. I'm going to give it a hydrogen because it had a hydrogen. I'm going to add a hydrogen, and then I'm going to put the R group. CH2, CH2, CH3, if I can squeeze that in there. I'm going to give the carbon-carbon a single bond, right? Now that carbon 2 was already bound to an R group. Here's the R group, CH2, CH2, CH3. It was already bound to a hydrogen. What else does it now have to be bound to? An OH. Okay. All right, now let's try the next one. Now this one, you kind of have to think about. So if I'm going to call this carbon 1 and I call this carbon 2, just for fun, we know that's not how to number them, right? Okay, but I'm just numbering them 1 and 2 because they're involved in the carbon-carbon double bond. So at carbon 1, how many hydrogens are attached? How many hydrogens? It is not 1. Everybody got a different answer. 0. There are 0 hydrogens. There are no, that looks like OH. There are no hydrogens, right? Do y'all see that? Because it's participating in 4 bonds. 2 in the double bond, 1 going this way, 1 going that way. So that makes 4 bonds. How about carbon 2? How many hydrogens? 1 hydrogen. So now, is there a difference in where I'm going to put the hydrogen and the oxygen and the hydroxyl? Yes. So this one, carbon 2 gets, I could spell, right? Gets the hydrogen, and then carbon 1 gets what? The hydroxyl. So let's redraw this. Now I'm going to erase. I'm actually going to number these correctly. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 carbons. Okay, so I guess we could change that. We'll make that carbon 5 and carbon 6. Okay, so this side of the molecule is the same until we get to carbon 5. Carbon 5 gets the hydrogen. So does anything change with carbon 5? No, he's still got the methyl, right? This is 1, 2, 3, 4, 5, right? He's still got the methyl. Now we're going to go up to 6. Here's 6, 7, 8. What else has to happen to 6? Oh, wait, what did I say? I said that wrong. Carbon 5 should get what? Carbon 5 should get the OH. Why didn't y'all say something? Carbon 5 gets the OH. Carbon 6 gets the H. Yeah? So sometimes it's nice to write this. Or this whole thing, sorry. So that you can remember, what am I supposed to add to what? Right? Okay. Go down to C. Let's talk about C. Let's give it 1, 2, 3, 4, 5. At carbon 1, how many hydrogens? How many? I think I heard it. 1 hydrogen. At carbon 2, how many hydrogens? 1 hydrogen. Does it matter what gets what? No. So we're going to draw our same little house. Carbon 1, let's give that the hydroxyl. And do I have to add my hydrogen? Excuse me. Do I need to add my hydrogen to carbon 2? Why not? It's skeletal. It's already there. How are we feeling? Good? No. Practice. And then if you need help, you can always ask me. Ask me for help. Try them. Try them. Okay, I think that was it, right? That's the end. All right. So let's summarize real quick. What were the 4 reactions we talked about today? Let's start from the beginning. Hydrolysis. Then there was condensation. Then there was hydrogenation, and then there was hydration. Okay. Let's talk about hydrogenation and hydration first. Hydrogen, right? You see the beginning? Hydrogen. What are you going to do in hydrogenation? Add H2 to an al what? Kene, which is a carbon-carbon double bond, right? What are you going to do in hydration? Dr. B really needs a glass of water to an alkene, right? Carbon-carbon double bond. Sometimes it's nice to just kind of summarize things for yourself, right? If we go through a bunch of different reactions, do this for yourself. Okay, now, hydrolysis, we're going to break water and do what? Decompose, synthesize, decompose an ester. What's an ester? ROR. So you're going to get ROR plus water. And sometimes they put it over the arrow. Sometimes they'll do it like this. They'll do, whoa, this pen is going a little crazy today. They put water like that. And then what happens? What do you get? We're going to decompose it. We're going to get ROH plus right? Okay, now in condensation, what's going to happen in condensation? So you have two molecules undergo what process? Decomposition or synthesis? Undergo synthesis and create water. Right? So you're going to have something that starts out as ROH plus HOR. And these two are going to combine. And when they combine in synthesis, you're going to end up with ROR plus what? H2O plus water. So that's 4 reactions that we did today. Okay, so we have hydrolysis, we have condensation, and those two are opposites of one another, right? Then we talked about hydrogenation and hydration. And what's the difference? What do you have to remember with hydrogenation? You're only adding a hydrogen to each, so it really doesn't matter. You add it to an alkene and you end up with what? An alkane. An alkane, carbon-carbon single bond, right? Okay, but with hydration, we need to be careful, right? So we're going to add hydrogen to the carbon with what? Carbon with more hydrogens, with more hydrogens. And you're going to add what else? Hydroxyl to what? To the carbon with more R groups. So sometimes making this little summary will really help you. And then when you're doing reactions, you can kind of come back to your summary page and go, okay, which one am I doing? Right? And it gives you kind of a roadmap on what to do. Yeah? Question? Okay. So let's go to chapter 6. So that wasn't the right one. Okay, so now we're going to talk about more carbon containing things, but in this case, we're going to talk specifically about sugars. And sugars are really, really, really important in metabolism of the whole body. So sugars are insanely, insanely important. Okay, remind me if I have, you should have watched the lecture. Did you watch the lecture? Yes, okay. So remind me if I have something that is, I'm gonna hide it. Maybe I'm gonna hide it. It won't let me hide it. Okay, so let's just come down here. If I have something, it's too much on the screen, that has one sugar molecule. It's just one sugar. What do I call that? A monosaccharide. If I have something that has two sugars hooked together, I have a disaccharide. Okay. If I have something that is 3 to 9 sugars long, what do we call that? An oligosaccharide. And then if I have something that is greater than 10, what do we call it? Polysaccharide. Okay, so that's your nomenclature that you have to remember. So jot that down. Okay, so let's come back up to the front. All right, so classify the following carbohydrates as mono, di, oligo, or poly, now that we know what things are. Raffinose, a soluble fiber containing 3 carbohydrate units. What do we call that one? Oligosaccharide, because oligosaccharide is 3 to 9. Starch, a storage carbohydrate of plants that contains thousands of glucose units. This would be poly, thousands would be poly, right? Plants use starch for glucose storage. What do we use? Glycogen. We use glycogen. Glycogen is a bunch of glucose molecules hooked together, but they're hooked together in a different way, and we'll talk about that. Okay, fructose, a simple sugar found in fruit with the formula C6H12O6. What is this one? This is C6H12O6. This is one sugar. This is a one ring, because all sugars, almost all sugars, look like this. They're this ring structure, right? What did we used to call this? So it's not a benzene ring, right? Because it doesn't have those double bonds on the inside of it, but it sort of looks like one. But instead of having those double bonds, what sugars have are alcohols and hydrogens coming off of the different carbons. And depending on which one it is, will tell you which sugar it is. So usually they have a complete ring, and then there's a carbon that comes off of the ring. And that's a typical sugar. Okay. So this is a one sugar, and a one sugar is a monosaccharide. Okay. Okay. So the next part is to identify things that are soluble or insoluble. And when we say soluble and insoluble, we mean soluble and insoluble within the digestive tract. So it's not like if you put it in water, is it going to completely dissolve? It's not asking that. It's asking what's going to happen actually in your digestive system. So the more things that you eat that are insoluble fibers, right, you feel more full. They kind of like turn into like a jelly almost. And so it increases the fiber in your diet, right? So oatmeal, this you just have to read and watch the lecture. Soluble or insoluble? Oatmeal is a soluble, it's a soluble fiber. So you have to go in and you have to go learn these. Brown rice, right? There's a big push to eat more brown rice than white rice, right? Because brown rice is insoluble. Okay, celery. Celery, we have a really hard time breaking down, a really hard time breaking down. This one is also insoluble. It's an insoluble fiber. Okay, so that one, those you just have to go, you have to go and learn those. Okay. So remember when I was telling you about the different functional groups and how important it was that you learn those functional groups? We're going to use them today. So they're going to be super important today. We're going to talk about alcohols. We're going to talk about all kinds of other functional groups that you should know by now. So when we're trying to classify things as alcohols, we can classify them as primary, secondary, or tertiary. How do we do that? What do we look for? Find your alcohol. So look at A. Here's my alcohol. Do I look at what's directly connected to my alcohol? No. I need to look at the carbon that's attached to the alcohol. So look at the carbon attached to the alcohol. Now, how many different R groups are attached to that carbon? This will be R1, R2, R3. So the number of R groups that are attached are going to tell you what it is. Count, so count number of R groups attached to the carbon. So is A primary, secondary, or tertiary alcohol? Tertiary. Okay, and B, I'm going to find my alcohol, and I'm going to go look for the carbon that's attached to the alcohol. Without me drawing it, what kind of an alcohol is this? Primary, secondary, or tertiary? Secondary. This is a secondary because I look at the carbon and I say this is R1, and then all of the rest is R2. Okay. And C, I'm going to find my alcohol, look at the carbon attached to the alcohol. How many R groups attached? Only one. This is R1. So this is a primary. Tell me about D. I don't want to write anything down. You tell me. D. Secondary. Good. Here's my alcohol. Here's my carbon. This is R1. And then the rest of this is R2. So this is a secondary. Not too bad, right? Got this. So got this. Okay. Now, do you remember the aldehydes and the ketones? See if I can scroll down. Do you remember the aldehydes and the ketones? So an aldehyde, this is how I remember. An aldehyde and a ketone look very similar. I drew an aldehyde and a ketone for you. Tell me what's similar about them. They both contain a carbonyl carbon. What's a carbonyl carbon? What's a carbonyl carbon? a carbon that is double bonded to an oxygen. So I have a carbonyl, and then I have another carbonyl. So in an aldehyde, how many R groups are attached to the carbonyl carbon? One. Poor, lonely, all alone in the aldehyde is only one R group. Look at my ketone. How many R groups are attached to the carbonyl carbon? 2. This is how I remember this. For a key to work, you need a lock and a key. So you need 2 things for a ketone, but an aldehyde is all alone. And when I talk about those things, I'm always talking about the R groups. So an aldehyde has 1 R group all alone. A ketone has 2 R groups. Need a lock and a key. Yeah? Let's see if we can apply that. So look at our first structure here. Find your carbonyl carbon. Where's my carbonyl carbon? Right here. So the dot that I put there is the carbon that's in the carbonyl group. So we call it the carbonyl carbon. So how many R groups are attached to that carbonyl carbon? 2. We have R1, and then the rest of this is R2. So is this a ketone or is this an aldehyde? Ketone. Okay, look at the next molecule. Find your carbonyl carbon. Here's my carbonyl carbon. How many R groups are attached to that carbonyl carbon? R1 is all of this, right? Is that hydrogen an R group? No, it's just a hydrogen. So is it a ketone or an aldehyde? Aldehyde. Okay, let's try C. Find your carbonyl carbon. How many R groups are attached to your carbonyl carbon? 2. R1, R2. Aldehyde or ketone? Ketone. Not too bad, right? Okay. We're doing good. Now we're going to apply this. You can have aldehydes and ketones as functional groups. And they exist as functional groups on sugars all the time. So it's really important to understand how sugars are made because it explains how they work in the body. Oop. Down here. Okay. So we're going to classify, these are monosaccharides. So sugars exist in one of 2 forms. They exist in a linear form, and they also exist in a ring form. What do you see here in A? Is that a linear form or a ring form? It's linear. It's a straight thing, right? So there are reactions where they become cyclic. They turn into a ring, and we'll talk about that later. But for right now, we're going to show sugars as straight chains. And that's what we see in all 3, in A, B, and C. So what we want to do is we want to classify these monosaccharides based on the type of carbonyl group and the number of carbons. So we're going to do 2 things. We're going to look for those ketones and those aldehydes, and then we're going to talk about the number of carbons. How have we talked about number of carbons in the past? Heptane, hexane, remember this? Butane, remember that? We're going to do the same thing, except instead of being an ANE, it's going to be a sugar. So in order for us to say that it's a sugar, we use OSE. Okay, so sugars end in OSE. So we're going to really say 3 things about the molecule in one word. We're going to say, is it a ketone or an aldehyde? We're going to say how many carbons are present in the sugar, and we're going to say that it is a sugar. Okay, so look at the first one. Do we have a ketone or an aldehyde? ketone. Here's my carbon that's participating in the carbonyl bond with the oxygen. I have one R group. I have two R groups, right? So that makes this a ketone. Lock and key, you need two things for a ketone. How many carbons are present? And you always start numbering. I'm going to give you this advice on the front end. Always start numbering as close as you can to the carbonyl carbon. So I can't number my carbonyl carbon number 1, right? So where am I going to put my number 1? Above or below? Above. So I'm going to go 1, 2, 3, 4, 5, 6. So do you notice that anywhere where you have that looks like a plus sign, there's a carbon in there? And it's just like on a skeletal diagram, there's a carbon there, okay? So how many carbons do I have? 6 carbons. What do I call something that is 6 carbons long? Hex, right? Okay, so now we need to put all this together. We need to say that it's a ketone, we need to say that it has 6 carbons, and we need to say that it's a sugar. So we're going to put all 3 together, and we're going to call this ketohexose. Ketohexose. So we have all 3 things together. Okay, take a second, take a minute, not a second. Try to name B on your own. Try to name B. I'm going to be quiet for a minute. Everybody got an answer? Almost. What's the first thing I should do? Well, and you could actually do any of the 3. Let's do it in the order that we did 1 in. Do we have a ketone or do we have an aldehyde? So I'm going to find my carbon that's participating in the carbonyl. It's bonded to one R group. All of this is an R group, and then it's bound to a hydrogen. So aldehyde or ketone? Aldehyde. So we're going to call it aldo. And then I need to count my carbons. So I'm going to start as close as I can to my carbonyl carbon. So I have 1, 2, 3, 4, 5. So what do I call this one? Pent. And then I know it's a sugar. I'm going to call it ose. Aldo pentose. Did y'all get that? All right. Let's try C. Find your carbon that's participating in the carbonyl. It's right there, right in the middle. So do I have an aldehyde or a ketone? This is a ketone. Start numbering as close as you can to the carbonyl carbon. Does it matter which one I start with? Not at all. 1, 2, 3. Okay, so I'm going to start with keto. What am I going to do next? Here's a question. Do I do those covalent beginning ones or do I do the alkane ones, right? Because remember, it was me, peanut butter, but then before it was mono, di, tri. So it's the mono, di, tri. Okay, so keto, triose. Isn't it really interesting though that you can look at a name and you can learn so much about that molecule just by looking at the name? And I mean, that system was designed that way so that there would be lots of information in a name. Okay, so now we're going to talk a little bit more about how monosaccharides are formed and how they exist. So remember when we were talking about stereochemistry, we were talking about mirror images and things like that. Do you remember that? Enantiomers and all that? Yes, a little bit. Yeah, okay. So in our bodies are designed for particular substances to metabolize certain things. And so we see this in sugars and we see this in amino acids. You can have things that are either the D or the L isomer. And the D and the L isomer is like the left and the right hand, right? And so your body's enzymes and everything in your body are designed for only one of the two. So in order to know which one is which, you have to be able to categorize them. So I think I put the instructions up here. Yep. So if you look at any given sugar, if you want to know if is it in the left hand or the right hand, that's the D and the L, right? You look at the carbon that is farthest away from the carbonyl carbon, but is still a chiral carbon. Do you remember the chirality rules? Do you remember how I said like all of this is going to build on everything I teach you? So in this diagram, do you see how some of the carbons we actually draw a C and some of the carbons we just represent as that plus sign? The ones that are the plus sign are chiral carbons. So it's very, very easy to look at a molecule in this kind of a drawing and say what's chiral and what's not. So look at A, look at that very first one. How many chiral carbons do I have? 2. Those are the plus signs, right? How many achiral carbons do I have? 2. I have one at top and one at the bottom. The top one's achiral because it's in a double bond. The bottom one's achiral because it's bound to 2 hydrogens, right? You remember this? Good. Okay. So if it is on, if you look at the carbon that is farthest away from the carbonyl carbon, but is still chiral. So in this case, in the first one, we're looking at this one. You're always going to have either a hydrogen or a hydroxyl bound to it. So you look for the hydroxyl. If the hydroxyl is on the right, it's a D. If the hydroxyl is on the left, it's an L isomer. Okay? So L is left, D is the only one that's your right. You know, why they couldn't do R, but you know, it's fine. Okay, so let's try this one. Here's our carbonyl carbon. I have 1, 2, 3 chiral carbons. Here's my farthest one, right? I find my farthest chiral carbon. And I look at the hydroxyl. Is it on the left or the right? It's on the right. So what do we call it? The D isomer. Okay. Here I find my carbonyl carbon. I find my carbon that is chiral, but that is farthest away. My farthest away chiral carbon right here. Look for my hydroxyl. Is it on the left or the right? Left. So what do we call it? L isomer. Okay. Here we find carbonyl carbon. Farthest achiral carbon right here. Find your hydroxyl, left or right? Right. What do we call it? D isomer. Okay. So put yourself a little set of instructions to find D and L. So D versus L, what do? Find carbonyl carbon, right? Carbonyl carbon. Go to chiral carbon farthest F-A-R-T-H-E, farthest from carbonyl carbon. If OH is attached on, I'm running out of room, on the left, this is the L isomer. OH attached on right, what are we? D isomer. If you write yourself a little, just a little brief instruction about what you're looking for each of the problems, it's gonna help. Yeah? How much time we got? Still got, good. Still got a few minutes. All right. So now, ooh, where'd it go? Oh, I just put it on the next page. Okay. So the next thing that we have to be able to do is we have to be able to switch between that D and L isomer. But when we switch between a D and an L isomer, you can't just turn the hydroxyl and the hydrogen on that carbonyl, on that chiral carbon. You can't do that. You have to do complete mirror images. So an enantiomer is something that is a complete mirror image. So what I want to do here, and I guess I can't really save this, but what you should do here is we're going to start like a set of definitions that's going to help you to kind of keep things straight in your mind. So an enantiomer is a mirror image, right? Mirror image. If something's a mirror image, everything that was on the left is now going to be on the right. Everything that was on the right is now going to be on the left, right? So this is you swap all left and right. And we're going to come back and we're going to add some more definitions to this as we go. So next time or whenever I say, you know, like go back to your definitions, this is what I'm talking about. So let's go and try and draw an enantiomer, which I already did those two. I did those two. Here we go. Okay. So we're going to draw an enantiomer of the following. Here we have D-fructose. So what you do is you draw the middle. The carbon backbone is not going to change. The only things that are going to change are the things that are attached to chiral carbons. So draw everything that is not chiral. So I'm going to draw CH2OH, right? This stuff is not chiral. I have all these carbons that are chiral, CH2OH, right? So now at each of these chiral carbons, what I'm going to do is everything that was on this side, it's on the left, is now going to be where? On the right. So what do? Let's fill in the right-hand side first. I have OH, H, H, right? Now, everything that was on the right is now going to be on the left. So H. Now, what do? Do I do this? Is that correct? No, because hydrogen can only make one bond. And here it looks like hydrogen is bound to the carbon and it's bound to the oxygen. So what do I need to do? HO, right? HO. So now I've drawn an enantiomer, a mirror image of D-fructose. So what should I call this one? If this is D-fructose, L-fructose. The only thing that changed was, is it a D isomer or an L isomer? How do I know that D-fructose is a D isomer? I find my carbon, my chiral carbon that's farthest away from the carbonyl carbon, and my hydroxyl is on the right side, right? This is on the right. That's the D isomer. in order to make the L isomer, I have to do the enantiomer. I have to do the mirror image. So I find my carbon, the chiral that's farthest away from the carbonyl, and I look at my hydroxyl. What side is it on? The left side. Okay, so that's how we do these mirror images, and that's how we shift between a D isomer and an L isomer. And I guess that's a good place to stop. And we'll do the other two the next time. So y'all remind me that we didn't finish that problem. We still got to finish 6.14. So just remind me next time. Y'all have a good afternoon. Any questions on Zoom? No, everybody left.